Hello everyone, welcome back to my channel, and in today's video we'll look into some AITS problems from mechanics. So the first problem is pretty good to revise, when and how to apply tau equal to I alpha. Give this problem a good try guys and then check out the solution. So basically in this problem we have a bead that is fixed on a rigid ring of radius r and of mass that is negligible as compared to that of the bead. Okay. Assembly thus formed is held motionless on a horizontal floor. So initially it is motionless and now it is given a slight push so that the ring starts rolling, and the coefficient of friction between the ring and the floor is given to be mu. So basically we have to figure out the angle rotated by the ring before it begins to slide and the speed of the center right before when it begins to slide. And they're not asking the speed of the bead, they're asking the speed of the center of the ring. Okay, so let's get to the solution part. Okay guys, so now let's say the bead actually rotated by an angle of theta relative to the vertical. So at this instant, so clearly the ring is going to have some angular velocity omega. So first let's begin by applying conservation of energy, because that's pretty trivial in this case. So the drop in height of the mass is this much, and that is this distance over here is capital R, and this small distance is capital R cos theta. So this black distance over here is capital R times 1 minus of cos theta. So the decrease in potential energy is mgr 1 minus cos theta, and this would be equal to the increase in kinetic energy of the system. Now as we are neglecting the mass of the ring, the ke of the ring, we can neglect it. So we only have to care about the kinetic energy of the bead. So the kinetic energy of the bead I'm going to directly write as half m times v1 squared. Okay, and here v1 is the net speed of the bead. So we have figured out the value of v1 in terms of theta. So we assumed an angular velocity of omega. Now the center of the ring is going to translate with some velocity. Let's call it v. Okay, now you can write the speed of the bead in two ways. So first you can either write it as a linear combination of v and r omega. So r omega is simply v, so and this angle is going to be theta. So you can write it as a linear combination, so and this angle is going to be theta as well. So the resultant of these two will be the net speed, and this actually forms a nice triangle. So as these two vectors are equal, resultant will be along the angle bisector. So this angle is theta by 2. So the resultant is simply v cos theta by 2 plus v cos theta by 2. So the net speed, which we termed it as v1, will come out to be 2v cos theta by 2. Okay, so this was method 1. Method 2, I'm not doing it. You can actually do it. So you can actually write the net speed by using the instantaneous axis of rotation. So you can simply figure this distance out using geometry, and then the net speed is going to be simply this distance. Let's call it r. So the net speed is going to be r omega. Okay, so now we can equate these two equations, and finally we, and write 1 minus cos theta as 2 sine square theta by 2. And finally we end up with this expression for the velocity for v and theta, and v was again the velocity of the center of the ring. Okay guys, so now if you can figure out theta, then we'll get the answer to the second question, which is the speed of the center. So now we have to determine relationships between accelerations and forces, right? So we have two tools actually. First tool is we can apply F net equals ma cm, right? So here again guys, mass of the ring is pretty negligible, right? So the center of mass, roughly speaking, will be at the center of the bead. So the thing is, if I want to apply F net equals to ma, then I need to figure out the acceleration of the center of mass, and the acceleration of the center of mass is going to be a bloodbath, and I'll give you kind of a hint to what it will be. To figure out the acceleration of the center of mass, the best way is to actually observe it relative to the center of the ring. So we know that the center of the ring, it can only accelerate in the horizontal direction, right? Let's call the acceleration of the center to be a towards the right. And why won't it have any vertical acceleration? Because the y coordinate of the point O is fixed, so it cannot have any vertical acceleration. So let's assume the acceleration to be a towards the right. So the center point will simply accelerate towards the right with some acceleration a, right? And relative to the center of the ring, meaning if you hinge the ring above the center, the bead will simply perform circular motion around the center. So, and if it's performing circular motion, then it'll have an omega square r acceleration, which is a centripetal component, towards the center of curvature or the center of the circular motion, and it will also have an r alpha component, and let's assume the angular acceleration of the ring is some alpha. So there will be some r alpha component of the ring, and r alpha we can also write it as a, because again due to no slip condition. So this is the acceleration of the center of mass relative to the center point O. So if we want to write it relative to ground frame, I have to add its acceleration vectorially to our center of mass. So as you guys can see, the accelerations, so there are three individual accelerations which we have to resolve evolve in the x and y direction in order to apply fnet equals to ma. So that's the reason why it's pretty hard to write fnet equal to ma in this case. Okay guys, so now if you want to apply tau equal to I alpha, you have to make sure of few things. So first thing is, if you don't want to consider pseudotorques, always apply tau equal to I alpha with respect to the center of mass of the system. So if you apply it with respect to the center of mass, then you don't have to consider pseudotorques, which will be the easiest in this case. But for some of you guys who might have used the point O or the instantaneous axis of rotation I, I'll give you some hint. So if you apply tau equal to I alpha by the point O, you need to understand that the point O is again an accelerated point. As we discussed, it has an acceleration of a towards the right. So as this is an accelerated point, you can only apply tau equal to I alpha about the point O, provided you take into account the pseudotorques. So relative to the point O, if you want to speak, you have to apply a pseudotorque of minus ma to the center of mass. And this ma will have a pseudotorque relative to the point O, as you can see. So in that net torque expression, you have to add the torque due to ma as well. Then this expression would be correct. And now for the instantaneous center of rotation, this point is also an accelerated point, because this point will have an acceleration of omega square r towards the center of the ring. And why is it? Again, you can use the same logic we used for the first case. Relative to the point O, this point I will move in a circle. Right? So relative to the point O, it will have an omega square r towards the center, and it will also have an r alpha towards the right. And now if I vectorially superimpose A to it, we know that A and r alpha should be equal for the no slip condition. So the net acceleration of the instant center of rotation is omega square r towards the point O. So the thing is, in the classic rolling problems, when we used to use the instant center of rotation, we used to neglect this fact, because if you apply the pseudotorque m omega square r, in the classic problems, it used to pass through the center of mass, which was at the geometric center. So in this case, as you can see, the line of action of the force, it directly passed through the instant center of rotation. Therefore, there was no torque because of this pseudo force. But in this case, you actually apply the pseudo force over here, right? It will be m omega square r, but its line of application is now shifted. So now, as you can see, with respect to the point I, it will have some clockwise moment, which you have to take into account if you want to write tau equal to I alpha. So anyways, the easiest thing is to write it about the center of mass, which is the bead itself. So the external forces acting on the system are, first of all, the weight of the bead, the normal reaction, and the friction force. So let's mark these forces. Okay, so there will be normal reaction, and let's say friction will obviously be in the rightward direction, guys, because clearly the alpha is in the clockwise sense, right? So A has to be in the forward direction so as to maintain the no slip condition. So friction will be in the forward direction, and in the limiting case, it would approach the value mu n. So mg I'm not writing, guys, because the net torque due to mg is 0, as it is passing through the point itself. Okay, so the torque due to normal reaction will be n multiplied by the perpendicular distance, and the perpendicular distance is r sine theta. So the torque due to normal reaction is n r sine theta, and the torque due to friction is going to be, will be minus, as it is in the counterclockwise sense, mu n multiplied by the distance from the point of application is going to be r plus r cos theta. So this comes out to be r 1 plus cos theta, and this would be equal to I cm, which is 0 in this case, because so the dmr square would simply become 0, as is a point mass. So now sine theta, I can write it as 2 sine theta by 2 cos theta by 2. 1 plus cos theta, I can write it as 2 cos square theta by 2, and this would be equal to mu. And from here, we'll get the limiting value of theta when friction becomes limiting as 2 tan inverse of mu. And at this particular theta, value of the speed of the center of the ring, we can find it by substituting it over here. And this comes out to be mu root gr. So the answer to this problem is B and C. Okay, so now let's move on to the next problem. Okay guys, so this question is a cat and dog chasing problem. Basically, a dog runs with a constant speed v, is chasing a cat that is running with a constant velocity u. So the cat's velocity vector is constant and the dog's speed is constant, meaning the acceleration of the cat is 0, whereas the dog can have some acceleration due to changing direction of the velocity vector. During the chase, the dog always heads towards the cat, meaning the velocity vector of the dog is always pointing towards the cat. And at an instant, the direction of motion of the dog makes an angle theta with that of the cat. So let's just depict it in a diagram. So let's just assume the cat is actually running horizontally and the speed of the cat is given to be u. So, and the dog is, let's say, over here somewhere. So the distance between the cat and the dog at this instant is given to be r. So this is the direction of motion of the dog, and it makes an angle theta with the direction of motion of the cat. So this angle is theta. So this is the situation. So we have to figure out the magnitude of acceleration of the dog, also the radii of curvature of the path followed by the dog at this instant. Okay, so now let's begin. Okay guys, so whenever we have to study acceleration, basically we have to study the rate of change of the velocity vector. So we have to see how the velocity vector is changing. We know one information about the dog's velocity vector is that it is always pointing towards the cat. So if the cat is present here, the v vector will be towards the cat, and when it is present over here, the v vector will be towards this red dot. So let's see how the velocity vector changes with time. So let's say after some time, so I'm going to get rid of all this. Let's say this is the initial point of the cat. After a small time, the cat's displacement is, let's say, u dt towards the right. Okay, as its speed is u, its displacement we can write it as u times dt. Now guys, initially the dog's velocity vector was along this line, right? Meaning the dog's displacement will also be along this line. So after a small time dt, the dog would have moved along the line. So this was the initial position of the dog, this is the final position, and this is the second position of the cat. So now the thing is, the velocity vector of the dog will point in this direction over here. So initially the velocity vector was in this direction, and finally, as you can see, it has rotated in the clockwise sense by some angle d theta. Okay, so let's call this angle again as d theta. Before moving on guys, let's take up a small concept. So if we have a constant vector whose magnitude is a, and let's say we rotate this vector by some angle theta, and we are keeping its magnitude constant once again, and let's say it rotated by an angle of theta. So now if I ask you guys what is the change in A, let's say this is the initial position, this is going to be the change in A, let's call it delta A. So now we can easily determine the magnitude of delta A. All we have to do is drop a perpendicular bisector. So this angle is going to be, these two angles are going to be theta by 2. So delta A, we can easily see it is 2A sine theta by 2. Now if I talk about infinitesimally small angles, so theta being very small, so, and I can also say delta A approaches dA. So from here dA is simply a d theta. Okay, and I'm calling theta to be d theta. And if I want a rate of change of A, all I have to do is divide it by dt. So dA by dt is nothing but the rate of change of A, and this comes out to be A times omega, where omega is the rate at which the vector A is rotating. So basically if we have a vector A that is rotating, let's say in the counterclockwise sense, its small change, let's call it dA, will be perpendicular to A, and this will be the new vector. And why is it perpendicular? It's perpendicular because otherwise modulus of A will change. If dA had a component along A, the modulus of A will change. Now if you guys observe something, dA is actually perpendicular to A and the omega vector. And if you do omega cross A, and again guys, omega is out of the plane in this case, if you guys would observe that it matches with the direction of dA. This, what we found out here, is the magnitude of dA by dt. If you want the exact form of dA by dt, it is going to be omega cross A. Anyways, the only thing we would require to solve this problem is that if we have a vector A and its magnitude is constant and it is rotating with some angular velocity, then its change is nothing but its magnitude multiplied by d theta by dt or omega. Okay, so now let's move on. So our current situation is also exactly similar. We have a constant vector v whose rate of change we are looking for, and it is rotating with some angular velocity d theta by dt. So the acceleration is basically the rate of change of velocity, and the rate of change of velocity we discussed in the previous page. This would just come out to be v omega in terms of magnitude, where omega is simply d theta by dt. So if we can figure out d theta by dt, then our question is done. Okay, and for that we'll use this differential triangle over here. Okay guys, so now this angle it makes with the horizontal is theta. This angle, let's just take it as d theta. So this angle will be theta as well because this line is horizontal. Now if I drop a perpendicular, these two lengths we can approximately say it's equal, because, and again guys, we're talking about displacements in infinitesimal times. Okay, so this distance is u dt, these distances are almost r. So this length over here, we can use the arc length formula and say it is equal to r d theta. We can also say it is equal to u dt sine theta, right? The sine component of u dt, and from here d theta by dt comes out to be u sine theta divided by r. I mean, there will also be a negative sign because technically d theta is reducing theta, right? The omega is in the clockwise sense, so it's reducing theta, but it doesn't matter. We can ignore the sign because we're talking about the magnitude. So the magnitude of acceleration will come out with the product of these two, which is u v sine theta divided by r. So this will be the answer to the acceleration. So basically at let's say at some instant the velocity vector of the dog was in this direction. So the acceleration vector dv will act perpendicular to velocity vector, and in a time dt it will change its direction by an angle of d theta. So now the thing is guys, the acceleration vector, it will always be perpendicular to v because the magnitude of v is constant, right? Now as we have to talk about the radii of curvature, so the radii of curvature at any particular point on the trajectory is nothing but the net speed at that point squared divided by the normal acceleration, where the normal acceleration is the acceleration normal to the velocity vector. Okay, so here the acceleration normal to velocity vector we already determined. It is uv sine theta by r. So we'll just substitute it over here and we'll get the answer as vr divided by u sine theta, and that comes out to be B option. Answer to this question is A and B. So now let's move on to the last question. So moving on to the last problem. So in this question we have a heavy steel ball that is held in contact with an extremely light steel ball at a height of h. Okay, so I think this distance is what they've given as h. The line joining the centers of the ball makes an angle of 30 degrees with the vertical if all the collisions are elastic and the sizes of the balls are negligible as compared to the height h. The horizontal range of the lighter ball is capital R and the speed just after collision is u. So we have to figure these two values out. So the initial height of the bottommost point of the heavier ball from the ground is given to be h. Okay guys, so now the thing is both of these balls are falling freely under gravity, right? So both of them will have an acceleration of g, meaning there is no force of interaction between these two balls, right? Both the balls have traversed a vertical distance of h. They will both have a velocity, let's call it u, of square root 2gh, right? And if some of you may have a doubt, how did this ball cover a height of h? You can consider both the balls as one single rigid body. So if one point of the rigid body covers a distance of h, then all the points would cover the same distance h. This ball also covered the same distance of h, and therefore all of them will have the same velocity of root 2gh. Or you can also use the time logic. They were freely falling for the same amount of time, so they will have the same velocity. Okay, so now let's forget about this for a while. So now we'll assume that the heavier ball collides with the ground first before the collisions between these two balls take place, and the collision takes a negligible amount of time. And just after collision, as it is elastic, the separation velocity would be the same as the approach velocity. So its velocity, so the velocity of the bigger ball will just get reversed. So it'll be u in the upward direction now. And now the thing is, we have to consider the collision between these two balls. And for that, guys, so the mass of the heavier ball is given to be much greater than the mass of the smaller ball. In situations like these, it's best to take the heavier ball as a frame of reference. So if I take the ball as a frame of reference, so if I draw it separately, it will have a velocity in the downward direction of 2u, again relative to the heavier mass. And the reason for taking, the heavier mass as the frame of reference is because the momentum of the heavier mass does not change appreciably. It does change it by a little bit, but it doesn't change it by too much. Like for example, let's say the impulse due to the heavier mass on the smaller mass is going to be j, and by Newton's third law, even on the heavier mass it will be j. So the change in velocity of this guy is going to be j divided by capital M, which is going to be a very small value because m is very high, right? So this guy's velocity won't change by that much, and that's the reason why we can take this as the frame of reference. Now the thing is, we know that as the collision is elastic, so normal line makes an angle of theta with the vertical. So the initial approach velocity, and also one more thing guys, the velocity of the smaller ball, it can only change along the normal direction. As there is no friction present anywhere, tangential velocity won't change. Okay, the relative tangential velocity will still be 2u sine theta. Whereas as the collision is elastic, the approach velocity, which is 2u cos theta, will simply change its direction. So it will be now 2u cos theta in the opposite direction. So this is how the final velocity, now let's get rid of this. So this is how the velocity of the ball after collision looks like relative to the heavier ball. So now as we want to figure out with respect to ground frame, we'll just add the velocity of the ball, which is u in the vertical direction. So now if you again resolve u, you can see the net velocity is going to be along the radial direction, it will be 3u sine theta, and along the tangential direction it will be 2 minus 1, which is going to be u sine theta in this direction. So this is the final velocity of the small ball relative to ground frame. This is the velocity in the radial direction. This is the velocity in the tangential direction. Okay. So now in the first problem, they asked us the net speed of the green ball. So the net speed, let's call it as v. It is going to be square root of 3u sine theta whole squared plus u sine theta squared. Wait, this would be cos theta. Okay, and after substituting all the values, you'll get the answer as 34.82 meter per second. So now we have to figure out the horizontal range of this green ball. So this green ball now only under the action of gravity, so it will perform a projectile motion. So we have to figure out its horizontal range from the point of projection. So here guys, we are going to make an assumption. As we don't know the height of this ball from the ground because the radii of the sphere is not given. So we are going to do the range calculations taking the initial y coordinate of the ball as the ground. So basically we're going to figure out this distance r and we are going to call it range. And this is obviously an approximation because in reality the range is going to be a bit higher, right? But the thing is, this is a very good assumption and I'll tell you why. So firstly, in the problem itself, they have mentioned that h is much greater than the sizes of these balls over in this line. On top of that, this green ball will actually rise to a height greater than h. And the reason for that is pretty easy. We can actually figure out the new vertical velocity. Let's call it Vy. So that will come out to be 3u cos square theta minus u sine square theta, right? And cos theta is going to be root 3 by 2. So this is going to be 2 actually. So as you guys can see, the vertical velocity has doubled after collision, which basically means new height to which it rises will be 4h. Because we know that h is nothing but u square by 2g. So if I double the initial velocity, the height to which the ball rises will be 4h. So the thing is, initially it dropped a height h, right? Now it's going to ascend to a height of 4h. So if I consider this is the ground, this is the big ball and this is the small ball, and this is actually performing a projectile which looks something like this. Okay, so considering this as our ground is a pretty good assumption is what I'm trying to say. So now let's figure out the range. So again, for the ball, we actually figured out the vertical velocity. It came out to be 2u. And the horizontal velocity, let's figure it out quick. So the horizontal velocity is going to be 3u cos theta, the sine component of it, plus u sine theta times the cos component of it. So this comes out to be 4u sine theta cos theta, which is 2u sine 2 theta. And sine 2 theta is root 3 by 2. So this is going to be root 3u. So the time of flight of the projectile is going to be 2 times the vertical velocity divided by g. And the range of the projectile is going to be the horizontal speed multiplied by the time of flight. And u square is nothing but 2gh using the first formula that we looked at. So the answer comes out to be 8 root 3 multiplied by height, which is 5 root 3. So which comes out to be 120 meters. Okay, so that would be the answer to this question. So that was it for this video, guys. If you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.